In this video, we're going to solve a complex circuit using loop current analysis. And this is a circuit that can't be simplified using traditional parallel and series circuit or resistor analysis. In order to solve this, we're actually going to apply Kirchhoff's voltage loop law a few times to basically figure out the current through every place in the circuit and then use that to figure out anything else we need to know. So let's get right to it. Our problem is actually going to be down below. We have this circuit here, has two little loops with two voltage sources over here. We need to find the current and voltage across that 5 ohm resistor. Our first step is going to be to label the polarity of all of the resistors. Now, this is a little bit of a weird one because resistors don't actually have polarities. There's no positive or negative side of a resistor. They work the same either way. The polarity is actually just going to be for us, and it's going to tell us about the voltage drop or possibly voltage increase across a resistor. And we can pick whatever polarities we want. I'm picking plus, the higher voltage, to be closer to the positive end of both batteries. But if we choose the wrong polarity, then we'll just get a negative sign in our answers later. So it doesn't really matter what we pick to be positive and minus. We're just going to have to use that to figure out the voltage drop later. Our next step is to draw two current loops that cover all circuit elements. And it might be more than two current loops that we need, but for this we only need two loops in order to get everything. There are three possible loops we can draw. I'm going to just pick two, and I'm going to have my first current loop going around in a circle here like this. I'll label that I1. And I'm going to have my second loop going around in a circle like this. I'm going to label it I2. Now I chose those directions so that it's the same direction as conventional current would be coming from this battery or this voltage source. That's because I think the direction is going to be that way. I don't necessarily know at this point, but hopefully it will be. And that way we'll end up with fewer negative signs. Okay, so here are our two current loops, and they do cover every single circuit element, so we are all set to move on. Next up, we have to use Kirchhoff's voltage law to write an expression for each current loop. In Kirchhoff's voltage law, as you probably remember, says the sum of the voltages around any closed loop is 0. So let's write our expression for loop 1. And if I start down here, we have sum of the voltages is equal to 0. We're going to get 10 volts plus, well, the voltage across this 8 ohm resistor. It looks like it's going to be a voltage drop, so I'm actually going to write it as a minus because I've said that it's going to a lower voltage. Minus 8 ohms times I1. And then, oops, I made a mistake when I drew my 5 ohm resistor with my polarity. Let me fix that quickly. And that I1 goes through the 5 ohm resistor. The 5 ohm resistor has two currents going through it, though. It's a voltage drop, so I'm going to do a minus 5 ohms times the total current is I1 plus I2. They're both going in the same direction, straight down. So that works out just fine, and that is equal to 0. Now we're also going to set that up for loop 2. So here's loop 2. Again, the sum of the voltages is equal to 0. We are going to have 12 volts increase minus 4 ohms times I2 minus 5 ohms times I1 plus I2 is all equal to 0. Now we have two equations with two unknowns. We're going to be able to use that to solve for our currents. But to do that, I'm first going to simplify this out quite a bit. We're going to have 10, and I'm going to get rid of the units just for simplicity's sake, minus 8I1 minus 5I1 minus 5I2 equals 0. That's the same as 10 minus 13I1 minus 5I2 is equal to 0. And that's about as simplified as we're going to get. Let's do the same thing on the other side. We're going to do 12 minus 4I2 minus 5I1 minus 5I2 equals 0. That's going to give us 12 minus 4I2 minus 5I2. Let's do minus 5I1 minus 9I2 is equal to 0. So now we have two equations, which I'm going to call 1 and 2. And they're pretty simplified. We can use all kinds of different methods to solve that system of equations, but we're going to need to eliminate one variable somehow. You can use substitution, you can use subtraction or addition, maybe division. I'm actually just going to use subtraction to eliminate I2. So I have 5I2 over here, negative 5I2, negative 9I2 over here. So what I'm going to do is I'm going to do equation 1 minus 5/9 times equation 2. And equation 1 is, of course, 10 minus 13I1 minus 5I2. We're subtracting off 5/9 times this other equation over here. That's going to give us minus, minus 20 over 3 plus 25 over 9 I1 plus 5 I2. And it's still all equal to 0 because we have 0 plus 0 on the right side. Now we have minus 5I2 plus 5I2. Those cancel. We can further simplify this out. 10 minus 20 over 3 ends up being negative, actually it's going to be positive 3.33 repeating. And then we are going to get minus 10.22 repeating. I1 is equal to 0. That's just from plugging things into a calculator and grouping up. So we get 3.33 is equal to 10.22, all repeating, times I1. When we divide out by 10.22, we get I1 is equal to 0.3261 amps. I'm using a lot of sig figs so that rounding errors don't compound. But there's I1. And it did end up positive. You do have to be careful about the signs here. Positive is good. That means we chose the correct direction way up originally when we drew our current loop. So now that we have that, we need to figure out what I2 is. And to do that, we can substitute back into one of our original equations. I'm going to substitute into, let's go with, into equation 2. Equation 2 is 12 minus 5I1 minus 9I2 is equal to 0. So that ends up being 12 minus 5 times 0.3261 amps minus 9I2 is equal to 0. We can simplify that, move our 9I2 to the other side, and we get 10.37 is equal to 9I2. And that means I2 is going to have to be equal to 1.15 amperes. So we're pretty close to being done. I'm going to move back up close to the circuit for the very last final answer. So let's come all the way up here. And for our final answer, we need to find the voltage and the current through that 5 ohm resistor. Well, we know that our current is just I1 plus I2. So that's easy to solve. I through the 5 ohm resistor is equal to I1 plus I2. So that's going to be equal to 1.15 amps plus 0.326 amps. And that gives us an I 5 ohms of 1.48 amps. 1.48 amps. Next up, if we want to find the voltage, we can just use Ohm's law now. V equals IR. The voltage across this 5 ohm resistor is going to be 1.48 amps times 5 ohms, which will give us a voltage of 7.39 volts. That's the voltage across our 5 ohm resistor. And that's that. We got a positive answer for this one too. That means we chose our polarity of our resistor correctly. It is going to be a voltage drop as we go down. So that's that. There's an example of using loop current analysis to solve a circuit. Again, we set up current loops to cover every circuit element, and then use Kirchhoff's voltage loop law. Substitute things in, and then solve a system of equations to find our unknowns. There's an alternative equivalent to solving this type of problem. It's called node voltage analysis, in which you look at voltages at different positions using Kirchhoff's current law instead of Kirchhoff's voltage law. And I'll show you that in another video.